Okay, we're looking at section I, the derivative of sine of x. Now let's review the sine of x first. So here we have y, which is going to be the sine of x, and this will be x. And let's put some values down. 0, 1, minus 1. And let's look at here pi over 2, pi, 3/2 pi, and 2 pi. Now to review the sine, if we look at a circle, the unit circle, if we look at the unit circle here, and let's put coordinates, here would be 1 and 0, here is 0 and 1, and here is -1 and 0. The first one is your horizontal. Now I'm not going to call that x because I would like to call the angle x. So we'll just here put an angle x and represent the point here having a horizontal component and a vertical component. Usually they call this theta, and they'll say this is the x component and the y component, but I'm already using x as the angle. So down here would be 0 and -1. All right, so if x is 0, then the horizontal is 1 and the vertical is 0. So for the sine, you want the vertical. So this one here is going to be your sine of x, this vertical, and the cosine of x is going to be the horizontal. So we start off here, the sine starts off at 0. And then as we go, as x goes from 0 to pi over 2, that would be 90, then the vertical goes to 1. Your vertical is 1, so we'll come up to here. Then we come back down to 0, and then we go -1, and then back up to 0. So we got something that's going to be like this here, like that. So that's your sine. Now let's look at the cosine while we're at it. So for the cosine, when you have x is 0, the vertical is 0, but the horizontal is 1. So you start up here. Now let's go ahead and label this one here the sine of x in blue, and we'll put the cosine here in red. And then when you have 90, you see the cosine will go to 0, so it'll be down here. And then as you swing over here, the cosine is going to be -1. That's going to be here at your pi. And then when you swing down, the horizontal component is going to be 0 again. And then when you come back here to 2 pi, you're back to where you started from. So you're basically doing this kind of thing, like that. Now let's go ahead and put in our pi over 2 here, and our pi here, and our 3/2 pi there, and our 2 pi there. Now, it's always good to have a picture of the functions we're considering. And I want to point out that the slope of the sine at 0 might be 1. Now, I'm not saying it's 1, I'm saying might. Well, that would be there. The cosine happens to be a 1 at that point. Now, let's look at this slope at pi over 2. Well, the slope there is 0. And look, the cosine has a 0 there. Here it looks like the slope might be minus 1, but look, the cosine has a minus 1. Here, the slope is 0 again, and the cosine is 0. Here, the slope could be plus 1, the cosine is plus 1. And we're going to find out that is the case. But it's suggesting here that it might be the case. It just might be the case. All right, so to do this properly, we need to use our master formula, which is going to be the derivative of a function f of x with respect to x is the limit as h goes to 0 of f of x plus h minus f of x over h. This is our master formula. Let's go ahead over here and just put in the values for x. Here would be a 0. Up here would be pi over 2. Over here would be pi, your x. And down here would be 3 halves pi. And when you come back to go here, it's 2 pi again. So you can think of the x as the points we considered: 0, pi over 2, pi, and 3 halves pi. And back up here, 2 pi, and we have the graphs. All right, now to do this, we need to know here for the sine derivative, the derivative of the sine, we need to have here replace the f with the sine function. So we're going to have the sine of x plus h minus the sine of x, and that's going to be over h. Now, we're going to need to expand this, and then hopefully we can subtract the sine of x part and then divide by h. That's the idea. Now, you may recall in trigonometry that if you have the sine, you can write that, expand that out. But what I would like to do, since my policy in derivations is to show all the steps, let's see if we can arrive at that. So we're going to do that by drawing here a rectangle. All right. So we have a rectangle, and I would like to here inscribe a right triangle so that this is a 90-degree angle. Now I know this is 90, and this is 90, and this is 90, and here if I extend that, this is 90 because they have the rectangle. And I want to make this line here, which is in the hypotenuse for this triangle, I want to make that 1. And then I would like to have this angle be x, and I would like to have this angle be h. So I have x, and then I have an x plus h is a bigger angle, and then later I'm going to consider this h, shrinking down, making this triangle such that the h angle gets to be, smaller and smaller. All right. So things will move around a little bit. You can just imagine another triangle that you have in there with a smaller h. But we want a general case. This keeps it general, so this is just fine. So now this line here is your cosine of h. So this is your angle, this is your adjacent side, and your opposite side is your sine. So I'm going to write the sine in for this one up here. Try to write it a little bit sideways, sine of h. So that fits in there, the sine of h. And then for this side, to get the cosine involved, this is your hypotenuse, cosine of h. And if I hit that with the cosine of x, I get this one down here. So this one is the cosine of h times the cosine of x. Now, if we look at this whole distance here, this whole distance here is the same as this distance here. I'll go ahead and put that in here with the dotted line. So this dotted line here, that distance is the same as this distance, the same as that distance. And see, that is the opposite side of the angle, and this is a right angle here. So that's a hypotenuse of 1, but the angle is x plus h. So 1 times the sine of this combined angle is going to be that vertical height. So that means this is going to be the sine of the quantity h plus x, or x plus h. And that is indeed what we have here, and we're going to break it up into two pieces, this piece and that piece, and you're going to see that we're going to be able to work this out. So if you look at this angle up here, this is complementary to the x because this is 90 and a triangle has 180. So that means the x plus, I'll call that z, is going to be 90. But notice that a straight line has 180 and this is taking up 90. So that means this angle and this angle have to be 90. And that means this one has to be x again, has to be the x angle. Now with this information, we're going to be able to get this piece and the lower piece. Well, let's look at the lower piece first. This piece here is going to be, if you think of this triangle, you have the angle x and you have a hypotenuse of cosine of h. So cosine of h times the sine of x will be this height. So this is the cosine of h times the sine of x, and that gets you this height. Now this little piece here, where we're going to look at this triangle, if you look at this triangle and here, and take the cosine of that x angle and multiply it by this hypotenuse, you will get that piece. Well, what is that hypotenuse? That is the sine of h. And then you need the cosine of that x to get that adjacent side. So that would be the cosine of x. So now we have our relationship. We know that the sine of the quantity x plus h is broken down into these two pieces. So let me write this out. So the sine of x plus h, that's this entire one, is going to be these two pieces. That's going to be equal to the cosine of h times the sine of x, and then plus the top piece, plus the sine of h times the cosine of x. All right. Now what happens to the cosine of h and the sine of h when h is small? Now I'm going to give a different diagram here to analyze this a little easier. All right, if we look at a triangle like this, where this is h in here, and this is 1, the hypotenuse is 1. Now if we were to swing this arc down like part of the circle, like making this part of the circle, then this would be 1 also, going out all the way to here. Now, what is the arc? In other words, what is this arc? Let's look at this arc. Well, if you recall, there's a nice relationship where if you have a radius r and an angle theta and an S, there's a nice relationship that says S is equal to R times theta. Now, let me review that. S is arc length. So this arc S, if you compare that with the circumference, which is 2 pi r. Now, I'm going to let this be r, but it is 1, but let's keep it in general for now. That has to be proportional to this angle theta to the entire angle 2 pi going all the way around. So the angle theta, this little piece here of a piece of pi compared to the whole angle of going all the way around, which is 360 degrees, 2 pi, that's in the same proportion as the arc length of the piece of pi to the circle. Now, in this case, I wanted to do this to show you that if you now look at how the 2 cancels the 2 and this pi cancels the pi, you then have S as r theta. So I wanted to show you where that came from. So this gives us readily this equation. Now, since r is equal to 1, then for our particular case, the arc S, this arc S, since this r is 1 and the theta is h, the arc is h. All right. So now we want to see what happens when the h gets smaller and smaller. Well, if the h gets smaller and smaller, you see that the cosine of h is starting to approach 1. So this is looking like we're approximately, for small h, we're approximately 1. And then here, this sine of h is getting very close to being this arc. As you get smaller and smaller, really small here, if we can like do an even smaller one, then the arc, if I try to draw the arc and that vertical line, it's like they're very close. So that would mean that the sine of h is approximately h. Now, it's important to note that this h is in radians. That's important. So now that we have this, we can see that in this equation, when things are small, this cosine is going to be approaching 1, and this sine of h is going to be approaching h. Now look what happens. If this is the case, when you put this up in here and subtract the sine, this term is going to go away, and then you're going to be able to divide by the h, and you're going to wind up with this cosine. So this is basically, what we're going to get. So this goes up into here, you subtract the sine of x, and since we're taking that limit, that cosine of h is going to be approaching 1. This sine will cancel this sine. We'll be left with this in the numerator, but the h can then divide that h, and you're left with the cosine. And that's indeed what we were seeing might be a possibility by looking at the slopes. So the derivative of the sine is the cosine. Now, this kind of a derivation will please the physicist or an engineer, but not really a mathematician. So let me give you a little more rigorous approach here. So if we do that, we're going to write down the derivative of the sine of x is equal to the limit as h goes to 0. And now I'm going to have to write down all this and minus the sine of x. So I'm going to take the time to do it all. So here's the cosine of h, just copying here, times the sine of x, and then plus the sine of h times the cosine of x. And now I need to subtract the sine of x, like this. and then go over h. So now we're going to have two parts here. I'm going to look at the part that has the sine of x in common, and then I'll look at the other term. So the derivative of the sine with respect to x here is going to be the limit as h goes to 0 of the cosine of h minus 1. I'm pulling out the sine like this. And that's going to be all over h. So we have the cosine of h, that's here, and then minus 1, and the sine of x, sorry. This is the sine of x, all right? So the cosine of h times the sine of x, first term, last term, minus 1 times the sine of x, all right? And then what's left is this middle piece. So that's plus the limit as h goes to 0. And that's going to be the sine of h over h times the cosine of x, which, since this involved the h here, I'm going to just emphasize that. And I can put that cosine of x in front if I want. Now, we're assuming here that the limit of this whole thing is equal to the limit of each individual part, and then add the limits. Now, in a calculus course, in the appendix, they usually have a proof of that. And they may not prove all that in the calculus course, but they at least include it in the book. So I'm not going to do that. You can refer to a calculus book to see the proof that if you have a limit of, let's say two things, because I broke this up into two things, that the limit of the two things is equal to the limit of each individual one, and add the limits together, all right? So we need to figure these out, and I want to figure these out a little more rigorously than just say the cosine of h is approximately 1, then that's gone, and the sine of h is approximately h, and that then gets you a 1. We already did that, so we do have a derivation in a sort of a loose, friendly kind of way. But now we're going to go more rigorous, all right? So to do that, I'm going to get myself a circle here, like that. And I'm going to look at here, going out like this, and say go up to here. All right, so now if we look at this, this is the angle H, and then here, this height in here, which I'll go ahead and put a dotted line like that. And let's emphasize that with a little different color, like this. That's going to be the sine of h, because remember that the radius of the circle is 1. Now notice that if we look at this larger triangle out here, so that's a right angle, and this is right angle here also. And if we were to extend this, we would have a right angle there. Then this height here is, well, look at this trick here. This distance here is 1. The radius from here to there is 1. But if you take the rise over the run, that's your tangent of h. So this is the tangent of h. This is the sine of h. And we know that the arc in here is equal to, h. Now what's going to happen when we get smaller h? This is the trick. All right. Well, let's look at some areas here. Let's say that we have this large area of this triangle, and we're going to call that large area, let's call that area, well, let's do like this. The area inside, the smaller one, let's call that area 1, that little triangle. Then let's call area 2 the area of the pie. So this is going to be the smaller triangle, and the area A3 is going to be the area for the larger triangle, and A2 we'll think pi. That's the piece of pie area. So if we look at those 3 areas, we can see that the small triangle has the least area, the pi is next, and the big triangle is the largest. So I'm going to write down A1 less than, I'm going to say less than or equal to, because as I shrink these down, we're going to find that they're going to be then approach equality. For the triangle in here, the small triangle, your triangle is your 1/2 the base times the altitude. So the base here is the cosine of h, and the altitude is the sine of h. So for this one, we want 1/2 we'll put the altitude first, sine of h. So 1/2 the altitude times the base. They sometimes give the formula that way, 1/2 AB, and altitude is A, and B is the base. So sine of h times the cosine of h. And that's going to be then less than or equal to the area of the pie. Now the area of the pie, we can do the area of the pie, that's the second one, by looking at the piece of pie, which has a radius of 1 and 1. Here's your angle. And if you want that area, we could say the area is going to be proportional by comparing the angle to 2 pi, the entire angle, and that's going to be the area of the pie compared to the area of the circle. Well, the area of the circle is pi r squared, which is 1. So that means the area of the pie, these pi's will drop out. This is going to be A2 over pi. And you can cross out the pi's. A2 is going to be h over 2. So this is going to be h over 2. And then the last one is going to be the area of the big triangle. Now that has an altitude of the tangent, and the base is 1. So that's going to be 1/2 the tangent times, well, 1. So we have it. So now what we're going to do is we're going to multiply through by 2. We can do that. With an inequality, you have to be careful, because you multiply by a negative, you have to switch things around, but 2 is positive, so that's not going to change anything. So we can then get this equation here. All right. Now what I'm going to do is notice that the tangent is the sine over the cosine. And what I want to do next is divide by the sine. I do want to do that because I'm going after this one here. So I can see that I got the h divided by the sine of h, and we get something similar to that. Now the sine of h, when h is small, is positive. Cosine's positive, everything's positive. So by dividing, we're not going to be changing any of the signs. So that is the cosine. When I say sines, I mean these inequalities. So cosine of h is less than or equal to h over the sine of h, less than or equal to, and then here I'm going to have just, if I divide by the sine of h, we're just going to have the cosine of h. Now, what I would like to do is flip these. Now you have to be careful, because if we flip them, say this is like saying something like, say 3 is less than 4 is less than 5. But now if I flip these 1/3 and have 1/4 and have 1/5, now the 1/3 is the big one and 1/4 is next and 1/5 is the smallest one. So now when I flip them, I need to change the less than sign to a greater than sign. So that's going to get me 1 over the cosine of h is greater than or equal to the sine of h over h, greater than or equal to cosine of h. Now, I would like to write this one first. So I'm going to simply write this as cosine of h first, and that's going to be less than, if I write it from the right to the left, this is going to be less than or equal to the sine of h over h, less than or equal to 1 over the cosine of h. Now, I'm going to take limits. So now the limit, as h goes to 0, I'm going to have here the cosine of h on the left, less than or equal to the limit as h goes to 0 of the sine of h over h, and that's the one I'm interested in finding, and that's going to be less than or equal to the limit as h goes to 0 of 1 over the cosine of h. Now I can take the limits of the extreme cases, because as h goes to 0, I have cosine of 0, that's a 1. So this is a 1. Now this is the one I really am trying to figure out, so I'm not going to worry about calculating that. I'm just going to write it down as it is. And then the one on the far right, I can let the cosine of h become cosine of 0, let it go, and I'll get 1. Now I'm seeing that the sine of h over h is less than or equal to 1, but greater than or equal to 1. So now it has to be equal to 1. So this is how we show that this is 1. Earlier I had said that the sine of h for small h is approximately h, and I, in a cavalier fashion, just canceled the h's and got the 1 that way. But this is a more rigorous one. This is called the squeeze theorem, where you squeeze that middle one, you get that squeeze between a left and a right, boundary, and you squeezed it in, and you find that it has to be 1. And now for the last piece is going to be this one here. So let me copy this one over again. The limit as h goes to 0, cosine of h minus 1 over h. And since the sine of x is independent, we're going to just work on this part here, and to show more rigorously that that's going to be 0, rather than just say, since the cosine of h is approximately 1 when h is small, then 1 minus 1 is 0. We're going to do it a little more rigorously. Okay, so what I'm going to do is multiply the top and bottom of this equation by the same thing. So I'm basically multiplying by 1. And that's going to be cosine of h plus 1 over cosine of h plus 1. So I don't change anything. All right. Now, when you have a sum and a difference multiplied together, you may recall you have an a plus b and an a minus b. You get a squared minus b squared. So that's going to get me here cosine of h squared minus 1. Let's look at that numerator here for a second. cosine squared of h minus 1, all in the numerator, that's simply minus the sine squared of h. Because remember, cosine squared of h plus sine squared of h is equal to 1. So here, the cosine squared of h is equal to 1 minus, this here would be 1 minus the sine squared of h. The ones would cancel and you would just have the minus sine squared of h. So let's write this out again with this in mind. And since I'm going to wind up with that minus sine squared, I'll put the minus sign out in front. And we'll have here the sine squared of h over h. And what else is down here? Well, we have cosine of h plus 1. And let's just make sure that we have all this in brackets. And I would like to regroup things slightly here. This is minus the limit as h goes to 0. I'm going to write the sine of h over h, and I'm going to put one of the signs over here, sine of h. So I still have my sine squared of h over h, and this will be cosine of h plus 1. Now, we talked about this earlier, that there are these things that can be proven in calculus class, and they usually have them in the appendix somewhere in the book, that if you have the limit of a sum, it's equal to the sum of the limits. If you have here a limit of a product, I'm going to consider this as one piece and this is another, that's equal to the product of the limits. All right, so I'm going to use that. This is the sine of h over h. And this is the first part. And then the second part will be the sine of h over the cosine of h plus 1. So here we have the two pieces, sine of h over h and the sine of h over cosine of h plus 1. And we're going to look at these limits separately and then multiply them together. Now this one we already figured out is 1. Now this one we can do because we could put the 0 in and you'll have cosine of 0 is a 1, so you'll have 1 plus 1 is 2. And when you put the 0 in for the h, you get 0. So this one is 0, which means that when you multiply the limits, you're going to get 1 times 0, which is 0. So indeed, this is 0. This one here, we showed to be 1. So the derivative of the sine is equal to the cosine. So all that goes away, and all this is 1. And this is a more rigorous derivation of the derivative. And I wanted to do that because I entitled this class, the course is called Calculus. So I want to be a little more rigorous than we would usually be in physics. In physics, we would have no problem just saying cosine of the angle h for small h is 1. The sine of h for small h is h. And then doing that, we would be happy with that. But this is a more rigorous derivation. Now, the reason why the physicists will do things like this, and engineers too, is that, remember, the final test for physics is experiment, is nature. So that's going to be the final verification. And if we were to be very strict and formal, like in mathematics, well, we would then technically have to prove the squeeze theorem using definitions of limits, deltas and epsilons, which I am not doing. We would have to prove all of these limit rules, that if you have the limit of a sum, it's equal to the sum of the individual limits. Same with the product, same with the division, same with, exponential, taking square roots and powers. You'd have to show all that. And that's a different discipline. That's what mathematicians do. That's mathematics. We need mathematics and physics, and you're required to take 3 calculus classes and differential equations for a physics major typically. So here, since my course is called a calculus, basic calculus, I like to be a little more rigorous than we would be in physics. And I'm not doing everything, but at least I'm pointing out things that I'm not doing, and where you can see them in the books, like the limit rules and proving the squeeze theorem with the delta and epsilon limit strict definitions, so that your critical thinking is sharpened and you know what we're doing and what we're not doing. But this is enough right up in here for a derivation, quick derivation, to keep physicists happy. We'll see you in the next class.